Today, I'm going to give a brief introduction about the bessel function. Bessel function is first defined by Bernoulli and then generalized by Bessel. First, we need to know about the Bessel differential equation. The general form of the equation is like this, where alpha is the order of the function. When we divide the entire equation by z squared, we can obtain the standard form of the equation, and the Bessel functions are simply the solution of the differential equation. To further know about the Bessel function, we can take a look at the Taylor expansion of the function. Take J0, which is the zero order of the Bessel functions, as an example. When we look at the result of the Taylor expansion, we can see that it's very similar to the series of cosine function, but the denominator of the coefficient is increasing when x increases. Therefore, the waveform of the Bessel function is just like a cosine wave, but the amplitude is decreasing. I won't go too deep in the mathematical part of the Bessel functions, but I'll move on to the application. In fluid mechanics, we have learned the Poisson's equations, which have the following assumptions. However, these may not be correct in our body, and today I'll focus on the fourth one, the steady flow. As shown in the graph, the pressure and the flow of the cardiac cycle is not steady at all. They are changing with time. When the oscillations in the pressure gradient are sufficiently slow, there is enough time for the Poisson flow to develop, and the profile at any fixed time will just look like the Poisson flow solution with the same pressure gradient, and therefore the time derivative terms in the Navier-Stokes equation may be neglected. However, in this case, the flow is a pulsatile flow. The pressures are functions of time, and time derivative term cannot be neglected. To solve it, based on the Navier-Stokes equation, after different assumption and calculation, we will obtain the unsteady flow, which obey a Bessel-like equation, like this. The detailed procedures of the calculations are not shown here. We can obtain the general solution with Bessel function J0 and Y0, which are the first kind and second kind of Bessel function. After applying the boundary solution, we can obtain a new profile. That is the woman's leaf flow as shown here. Thank you.